Hello, a nice quick video this time. Let's look at isometric tiles. And as usual, a quick demonstration of the application before we get going. The isometric approach to tile rendering gives it a pseudo 3D feel. So here we can see I'm selecting tiles, but the tiles are no longer axis aligned or aligned with the edges of the screen, so that adds some complication about working out which tile is currently highlighted. And you can get an appreciable feel of depth by using sprites that are larger than the tile itself. So here we've got some trees being planted, different type of tree there. And all of this simple demonstration is going to do is allow us to scroll through a fixed selection of tile types. I really want to keep this one nice and quick and simple. Working with conventional 2D tile maps is something we have done many times on the One Lone Coder channel. We would assume a world that looks like this, and here we would have an x-axis, and here we would have a y-axis, which would imply we have an origin at the top left here. Once we establish that our tiles have a width and a height in screen space, i.e. how many pixels of the screen the tile occupies, we can then quite easily translate the mouse location into the discrete form required to access the array that represents this tile map. So assuming our mouse cursor is somewhere here, we can take this mouse coordinate, let's call it mx and my, and what we want to work out is what is the coordinate of the cell that the mouse is within. And this has always been simple because we allow integer division to sort all of this out for us. So we can assume that cell x is equal to the mouse's location x integer divided by the tile's width. And it's the integer divide that's important because that will give us a whole number and discard any remainder as part of the division. So that will always give us a location that represents the cell. Conveniently, we can do exactly the same for y, but this time we'll do an integer divide by the tile height. It could be that your tiles are square, but I prefer to program it in a more flexible way. Sometimes it's also convenient to know where does the mouse lie within that particular cell. Well, that's trivial too, so let's assume this is called offset x. We can take our mouse coordinate and we'll take the modulus with the tile width. So this will give us a offset in screen pixels of how far the mouse coordinate is into the tile. And naturally, we have a corresponding for y. Sometimes it's helpful to normalize this value by dividing as well by tile width and tile height to give us a value between 0 and 1 to represent where the mouse is within the cell. And if we know the overall width of our world, then we can easily take our cell's x and y location and convert that into a one-dimensional index into an array that represents this world. We have done this countless times on the channel. It is simply going to be I equals cy times width plus cx. For regular viewers of the channel, all of this should be very familiar. When working with isometric tiles, the rules aren't quite as simple, simply because there is no axis alignment anywhere in our world map when rendered on the screen. So I'm going to make some assumptions that up here is our 0, 0 coordinate, and along this edge is our x-axis, and along this edge is our y-axis. The first problem we have is that a particular tile is no longer square, and so transforming the mouse coordinates as we did before is no longer really that applicable. Secondly, if we look at adjacent tiles in this map, we see that they aren't necessarily adjacent in the isometric map, and so we need to think of things a little differently. I've created some rudimentary isometric tile graphics, and it's quite important that to get my approach to work, I'm going to make an assumption that the aspect ratio of my tiles is 2 to 1. So the tile fundamentally is going to be twice as wide as it is high, and in this instance I've chosen tiles which are 40 pixels wide and 20 pixels high, and I've created a selection of them. So along the top here I've got a highlighted yellow one which will represent which one the cursor is over, I've got an empty tile, I've got one filled with grass, and I've got some larger tiles here at the bottom which are populated with simple objects. So let's start at first by simply rendering a plane of empty isometric tiles. As usual, I'm going to use my Pixel game engine to do this. So I've created a class called Isometric Demo, and it doesn't have anything in it yet other than it will clear the screen to white. So we don't load anything on user create, and per frame all we're drawing is the background. The window itself is constructed to be 512 pixels wide by 480 pixels high, and each pixel is going to be represented by 2 screen pixels. Fortunately for this demonstration, there isn't very much code, about 100 lines. I'm going to start by adding some variables that describe the world. So here I've added an integer 2D vector to describe the size, which is going to be 14 in the x-axis and 10 in the y-axis. As established, my isometric tiles principally are going to be 40 pixels wide by 20 pixels high. And I'm going to establish that the origin of my world, that is, where should the 0, 0 isometric tiles start to be rendered, is going to be at 5, 1. And that means 5 isometric tiles across and 1 down from the top left of the screen. I know I've got some graphics data to load, so I'm going to create an OLC sprite pointer to store that. And I'm going to create another pointer to store the 2D world array. In onUserCreate, the first thing I'll do is load my PNG file that contains my isometric tile data. It contains all of those sprites, and we'll use the draw partial sprite to extract regions of it to draw to the screen. And then I'm going to initialize my world array depending on the size of the world that we've specified earlier, and I'm going to make sure that that's defaulted to all zeros, which is going to represent an empty tile. For each frame, the first thing I'm going to do is clear the screen. And I know I'm going to render the entire world for this application. We're not going to do any clipping, so I'm going to create 2 nested for loops that iterate through all of the cells in the world. In this instance, I've chosen to render Y first and then X because I want to render from the top of the screen towards the bottom. And this is because conceptually the bottom of the screen is closer to the player than the top of the screen, so we want objects at the bottom to be drawn last. We've already established that the world does not exist in the same space as the screen, so we're going to need a transformation function. I'll call that toScreen and populate it in a minute. But ultimately, that should give us a 2D coordinate of where to draw a particular isometric tile on the screen. Now we just need to decide which type of tile we should be drawing. And so here I'll take the Y coordinate and the X coordinate and the width of the whole world to index the pworld array. If the value of the array at that location is 0, that's going to be a blank tile. I've called it an invisible tile here, and I'm going to use the Pixel Game Engine's draw partial sprite function, pass it to the transformed coordinates of the world so it's in screen space, and then select the appropriate sprite out of the sprite sheet I showed earlier. And for now, that's it. Because I have a feeling I'm going to be using toScreen in several different places, I'm going to create a small lambda function to do that transformation for me. And I'll put that up here. So this will take in an X and a Y in world space and give me the screen coordinate in return. The image file I'm using has transparency. It has 2 types of transparency. One is simply there is a transparent pixel or there isn't. And with this glowing rectangle, we've got varying degrees of translucency per pixel. The Pixel Game Engine can render these differently, and it's more optimal to choose the appropriate method before trying to draw the sprite. Since most of my graphics have a binary alpha value for the pixel, I'm going to use the masking mode of the Pixel Game Engine to perform the rendering. This means if there is a pixel with any transparency at all, it won't draw it. And it's important that when you start playing with the pixel modes that at some point you set them back to normal because they're persistent once they're changed. Now let's have a look at this transformation. To start with, we know that each isometric tile is in fact a 2-dimensional sprite. And so, even though the tile's coordinate exists here at the top center, the sprite coordinate actually exists here. And therefore our transform will take this world coordinate and generate this screen space coordinate in return. We can deduce this transformation empirically just by looking at the data. Starting at 0, 0, we know the sprite needs to be in this location. And relative to the world origin, this is half the sprite width to the left. If we increase just in the x-axis of world space, our next sprite is here. So we have moved along half the tile width, and we've also moved down half the tile height. And this is true for all increments in x. So we can make an assumption that our screen x coordinate contains a component like this. World x multiplied by tile width over 2, and our screen y coordinate similarly has x multiplied by tile height over 2. However, our world is not one-dimensional. We're not going to just traverse along the x-axis. We also have a y component which also influences both the screen x and screen y locations. So via a simple analysis again, if we increase in just the y-axis, we can see we've moved backwards 1 tile width over 2. And we've also moved down 1 tile height over 2. So as y increases, we're going to move backwards in x. So I'll subtract the y component, also tile width over 2, but I do move down the screen, so it's plus the y component, tile height over 2. Hopefully it's easy to see that these can be rearranged to the form Sx is therefore x take y multiplied by tile width over 2, and screen y coordinate is x plus y tile height over 2. We're almost done here, but we must realise that the origin of the world in screen space is no longer the top left of the screen. So we have to also offset our screen x and y position to this origin location. This means our toScreen lambda transform function isn't very complicated. I'm going to make it return a integer 2D vector. And here you can see I've taken the origin and multiplied it by the tile size, and to that I add the offsets we've just calculated. And as I iterate through each location in the world, I calculate its screen position and I draw the sprite. So let's take a look. Very nice. We specified that the world was 14 along the x-axis, which is along here, and 10 along the y-axis. I've chosen those numbers just so the whole world fits on the screen. You can, of course, implement your own panning and zooming using this approach. But this video is specifically about how do we select the tiles. And well, tile selection implies that we need some mouse information, so I'm creating a 2D vector and populating it with the mouse location in screen space. As I demonstrated at the start of this quick video, we can work out approximately which cell the mouse is in by using integer division. Now that doesn't necessarily make much sense right now, but bear with me and I'll explain shortly. I also want to calculate the offset into the cell, and you can see I'm using the modulus operator to do just that. But hang on a sec, these cells are in screen space. In fact, let's draw where this cell is to visualize this effect. To draw the cell in screen space we're currently hovering over, I'm just going to draw a rectangle at the cell's location multiplied by the size of the tile. And I'm also going to throw in some on-screen text so we can visualize the coordinates. So here you can see as I move the mouse around, a screen cell is selected. And if I move to the top left, it even says cell 00. This is something we've done many times. This is traditionally how you would work with a 2D tile map. But you'll notice that the cell only rarely lines up with a tile in our isometric grid. And so it isn't actually possible for me to get the rectangle to go on alternate adjacent tiles. Also, the cell value doesn't make much sense either. Here, in world space, this should be 00, but we can see that that's cell 51, and that's because we've offset from world space to screen space using our origin vector. And as I move along the x-axis, we can see both cell values are changing. Clearly the cell coordinate is not in world space. I'm going to add another vector called selected. And this vector, I'm not going to use a lambda function to do it, but we do need to have a method of transforming the cell in screen space back into world space, and that will of course then represent our selected cell in the isometric tile. The process for working out this transformation is not too dissimilar. Here I've drawn our screen space cell grid overlaid with our world space isometric grid, and particularly this cell in the middle here in world space is 1, 1. Let's observe what happens as we transition around screen space. As I move up 1, in world space I have decremented in both the x and y axes. And as I move downwards, I've incremented in both the x and y axes in world space. As I move left, I have decremented in the x-axis, but incremented in the y-axis. And as I move right, I have incremented in the x-axis, but decremented in the y-axis. As before, we're going to need a transformation that takes our now screen cell space coordinate and transforms it into a world coordinate. And again, it's a multi-component equation, as both x and y in screen space factor into the individual x and y's in our world. Given that we already have the cell value, we no longer care about the tile width and tile height. So let's again consider our x component first. We'll call it world x. straight away we can see that our world X coordinate directly aligns with our cell Y coordinate. So taking the origin into account as well, we know that world X is going to be reliant on CY minus origin Y. We also see that our world X coordinate directly aligns with our screen X coordinate, which is very convenient. So we can simply add that as well. And in a similar fashion, we'll calculate the transformation for Y. In just the same way as X, we see that our world's Y values are directly in line with our screen cell Y values. So that's just a repeat. But this time, our world Y values are going in the opposite direction to our screen X. So you can see here they're actually decrementing as our screen X is incrementing. Therefore, very simply, we're going to subtract our cell X value, accounting for the offset. So I'm just going to paste that directly into our transformation. And at the bottom of the program, I'm also going to output our selected cell value. After we've drawn the world, I want to draw the highlighted selected cell. This cell had multiple levels of alpha in it. So I'm going to use the Pixel Game Engine's alpha blending mode, which is slow, but we're only using it for a handful of pixels. The current selected cell coordinate is in world space, so I'm going to use the toScreen lambda that we created earlier to convert that to screen space. And then I'm going to draw the required graphic on top of what is already there. So up here we'll have drawn the contents of the tile, but down here we'll then overlay the contents of the tile with a highlight. So let's take a look. Well, we can see that the highlighted cell is certainly being drawn wherever the red rectangle was before, so that implies there hasn't really been any different. But what we can see is that the selected cell value now, this coordinate up here in the top left, accurately reflects the selected cell in the world. So as I move along this top edge, that's our x-axis, we can see that that's increasing, but our y value doesn't. And similarly, if I move along the y-axis, we see that's increasing, but our x value doesn't. And we see that it actually works for anywhere in the screen. So we'd probably want to put some boundary checks in later to make sure we can't choose elements that aren't in our world array. But there's a problem straight away. I can only select the cells that exist in the rectangular cell space of the screen. How do I select these ones in between? See, I can't select it. And well, the answer is quite simple. We're going to cheat. Recall that we now know which cell in screen space our mouse exists in, and we've managed to work out which isometric tile in world space that screen cell corresponds to. The problem is we can't access these tiles because they don't fully occupy a cell in screen space. We also managed to work out where the mouse exists. So we know that the mouse must exist somewhere in this cell because that's given us this coordinate here. And we also worked out the offset of the mouse into the cell. Therefore, if we could detect that the mouse is in this region, or this region, or this region, or this region, we could bias our world coordinate accordingly to either increment or decrement along the x-axis or y-axis. There are several approaches to this, and you may expect, because of the nature of this channel, that we'll now do some geometry and look at line intersection equations and which side of the line a point lies, but no, I'm going to really brute force this. And I do it by creating a cheating tile. So here I've created a solid tile. It's the same dimensions as my other isometric tiles, but the regions in the top corners are identifiable by a unique colour. And since this tile represents an on-screen cell, and I know the offset of the mouse into this cell, I can determine quite easily which corner of the cell my mouse lies in just by looking at the colour by sampling that sprite at that location. We've already got the offset into the cell of the mouse, so I'm just going to call the getPixel function on the source sprite at that location. It's offset a little bit because this was a sprite containing all of the sprites, but it's sampling from the right location to give me a pixel value. And then once I've worked out what my selected cell is, I'm going to modify that location by looking at the returned pixel colour and adjusting the x and y value accordingly. Let's take a look. So now we can see as my mouse goes into the corner of the screen cell, it's selecting the appropriate world cell underneath it. And therefore I can put my mouse over anywhere in the isometric tile array and accurately get the cell underneath it. Let's just finish off this quick demonstration by adding the other graphics. Firstly, I'm going to stop drawing the red rectangle. We don't need that anymore. And now that we have the selected cell accurately in world space, I'm going to be responsible to the mouse button being clicked. And all the mouse button being clicked is going to do is increment the integers stored in our world array at that location. I'm also wrapping it round to the total number of sprites available. And because our selected world value can be anywhere, I'm going to guard our array with an if statement to make sure that it's within bounds. And the bounds are in world space too, so I don't need any fancy transforms for that. I'm just comparing with the world size we specified at the start. Since the value of the graphics can now be something other than 0, we're going to choose the appropriate sprites depending on their value. There's nothing especially clever going on here, but I will draw your attention to the sprites that exist along the bottom of the image. These sprites are effectively 2 isometric tiles high, so I need to offset it by that before I draw it to make sure that they draw in the correct location, because I don't want to just draw the top half of this tree where the tile should be. And so if the tile at a particular ID has height, I'm taking that into account. And so finally, we can now click on a particular cell to colour it in, and the more times we click on a cell we increment the cell's value, allows us to scroll through the graphics. And as we're always drawing from top to bottom, we can be assured that things closer to the camera are drawn on top of those further away, giving that lovely feel of depth. And so that's that. A quick and simple method of getting away from always having to use a top-down 2D tile perspective in your games. You can add some pseudo 3D retro loveliness without much code or complexity at all. As usual, the source code for this project can be found on the GitHub in the link below. I've just updated the Pixel game engine, so make sure that you have too. If you've enjoyed this video, a big thumbs up, have a think about subscribing, come and have a chat on the Discord, and until next time, take care.